Pablo. Welcome back again to a new YouTube video. In this time, we will talk about segment routing traffic engineering and basically how can we instantiate our policies of segment routing traffic engineering using the feature that we discussed in the last video, which is basically the feature called performance measurements. Okay? As we recap in the last video about performance measurements, we saw how it works, performance measurements, why it's needed, and how we can configure in the network devices. But also in the previous video, we didn't discuss how we can actually make use of this feature by using segment routing traffic engineering, right? We know that this feature is very useful to capture latency and also packet drops, right? And actually, with those metrics, we can basically provide a better treatment of the IP SLAs for our customers. So we can direct the traffic of the customer over the low latency paths, for example. Okay? So in the previous video, we discussed and explained a little bit about performance measurements. Now in this video, what we will focus is how we can make use of that once we have already captured the latency in the network, how we can make use of that latency captured, and based on that, how we can tell and create segment routing traffic engineering policies for particular customers to basically determine and create a traffic engineering path over the low latency links. Okay? So basically our task for today will be to configure segment routing traffic engineering by making use of the latencies that has been captured by performance measurements. Just as a brief introduction, as we discussed also in the previous video, and you can actually watch it if you want to have a broader details, performance measurements is enabled per link, right? And every device in the network capture the latency towards the other device, basically the one-way latency. So for example, P1, when we have performance measurements enabled, P1 capture the latency that it takes him to reach provider 1, and also it captured the latency towards provider 2. Okay, so but that's basically the metric that performance measurements give us. Now, as we also saw in the previous video, this metric is exported into the ISIS or OSPF network, and that's how every device in the network knows about the latency of every single link. Okay, so for the work today, what we will do basically, and to show how we can actually make use of the traffic engineering with performance measurements, we will focus on this piece of the network. Okay, so we have enabled performance measurements in the link, in every single link. We have enabled in all the network. In our case, we just enable between the links of provider 1 and provider H1 and provider 1. So in this link, we enable performance measurements, and also we enabled performance measurements between these two links. So basically P1, provider 1, and P3, every of them export their metric into the ISIS. Okay, so every device knows about the latency across every single link. Also, what we have in this network to basically create our use case of segment routing traffic engineering, we have segment routing enabled in all the network. Okay, basically P1 has also a loopback 1111, P3 has a loopback 3333, P1 has the prefix seed for the loopback 16001, and P3 has the prefix seed 16003 in segment routing. Provider 1 doesn't have any prefix seed enabled, simply is enabled with segment routing in the network. Okay. Also, to sum up more into the test, we have a customer here. This interface actually, well, not really the interface, but we have a loopback. I think it's a loopback 100. Under that loopback, we have the BRF VPN, and there we configure an IP address to emulate that we have a customer in P1. And in P3 we did the same. We have the loopback 100, and we put this loopback under the BRF VPN, and we also put an additional IP address under this interface. And also to pass obviously the customer routes for those VPNs, we have BGP, IBGP sessions between P1 and P3. So this is multi-protocol BGP sessions between them, and they are using the loopback 0 as a BGP neighbor. Okay, so we have the customers in the loopback 100, the VRF VPN. We have also in the underlay ISIS, of course, as the IGP protocol, passing the routes and enabling the necessary features for segment routing and for segment routing traffic engineering that I will show you in the configuration. We have also perform measurements enabled under the interface to capture the latency, and we have segment routing on top of that with the prefix seed that I just mentioned to basically create our label path. Okay, so what we will do now in the lab is we have all of these already enabled. After we revisit the configuration, we will see basically show commands to see the latency that perform measurements share under the ISIS database. I will just switch here the color. Also, we will see, once we know the latency, we will see that that latency is also exported under segment routing. So segment routing is aware of all the ISIS topology, including the latency that is exported as well in ISIS by perform measurements. The last two but not least, we will use this latency to create a traffic engineering policy from P1 to P3. Okay, so we will enter into segment routing traffic engineering. We will use ODN. Also, I have a video about ODN in my YouTube channel, so you can go and take a look. I will put you in this screen close to what you will see now. And ODN basically is the way that we can instantiate segment routing traffic engineering policies manually, automatically, dynamically. So we will configure ODN for basically all the prefixes that are with the color 100. We will, I just wrote this, yeah. We will, all the prefixes that comes with the color 100, we will basically choose the path that will be low latency. Okay, so P3, we also configure that P3 will send all his VPN routes that is configured over here with a color 100. So when P1 receives these VPN routes with color 100, P1 will have the ODN policy, on demand policy, matching those prefixes with the color 100, and once those prefixes are matched, then P1 will choose the path with low latency. And how it will know that the latency across the links and choose the lowest latency across the links? Well, because we have perform measurements enabled. Okay, and we will see that the policy will be up. Of course, in my network, I just have these 3 devices. I just wanted to make it easier for you for understand the feature, how to configure, how easy it is to configure. And in the next videos, we will do a bit more complex topology. But for now, I just wanted to give you the whole overview of the network. Okay, so without going into more explanations of the topology, I will just go to P1. And here we will see that we have, just real quick, we have ISIS configuration. The ISIS process in P1 is SRMPLS. We have the net ID. This command is very important for enabling traffic engineering. We need to distribute all this information that we export in ISIS into all the domains. So that's why we need this command, distribute link state level 2. We also need metric style wide. That's a very important requirement as well for being able to do segment routing traffic engineering policies. And of course, here I was in the provider, I was here in this device provider 1. I was not in P1. I'm so sorry for that. But yeah, since we are here, just let's recap this configuration. So basically the same distribute link state, it has to be also in the provider devices. And this provider device has metric style wide that is also very needed. And also a very important requirement in segment routing traffic engineering is that you need to have the interfaces tagged as a point-to-point network type. If it's not as a point-to-point, then segment routing traffic engineering will not work. So 3 important requirements for SRTE to work properly in all the networks: point-to-point under the physical interface, metric style wide in the ISIS process for address family IPv4, and distribute link state as well has to be enabled. Okay, this is in provider 1. Also here I have configured the segment routing global block. Sorry, segment routing MPLS global block. This is already configured by default if you don't enable, but it's best practice always to enable the default range, which is 16,000 to 23,999. It's always best practice. Okay, so we saw now provider 1. Let's jump into provider PE1. Okay, so here we have the same process of ISIS. We are now in PE1. We have also the IS type level 2. We have also the distribute link state, but this is important, I was saying, for exporting these metrics into segment routing. We have metric style wide, also a key requirement for SRTE. We have, of course, segment routing, similar as provider as well in the middle, PE1. We have the prefix seed, that this is very important as well to enable segment routing. We have that enabled, and the physical interface as a point-to-point. Okay? And also here I enabled the segment routing global block, which is this one here. Please ignore SRv6, will be in the next video. Okay? So a part of that, just to show you a little bit more, I have created a BRF in PE1, that is VPN, is the one that I show you just in a little bit. And with the route target export and import. And also I create in BGP, as I told you, neighborship with router 3, P3, 3333. The address family is VPN because we are exchanging VPN routes. And pretty much that's it. It's an IBGP session under the BRF configuration. In P3 is pretty similar configuration. Not much science, to be honest. We have just the similar ISIS process with IS type level 2. Distribute link state is very important. Segment routing is preferred as well. The prefix seed, which is also important for segment routing to configure, and always never forget point-to-point in the physical interfaces. Okay. Also here I have the VPN BRF, BRF VPN with the route targets similar as the other, and here in BGP similar as P1, but obviously with different network addressing. I have a neighbor to P1 to establish the IBGP sessions, and I enable the VPN before here. Okay, so the same, I created my customer, which is VPN under BGP, and here I basically redistribute my loopback. That is 100, I believe. We will check that we share to the P1. Also, I told you that we will use ODN. So ODN, we need to receive the prefix. P1 basically needs to receive the prefix from P3 market with a color. So P3 is marking the prefix with the color 100. So here we have a route policy that does it. And with the route policy, I have basically set the color 100. So if I do extended community set color opaque color, then I have the color 100 enabled. Okay, so how I can color and create my policies? Just create the extended community with opaque, with a name. This is a way that I can color and assign color to my routes. I put the color 100 and I put this under a route policy, and the route policy in the outgoing direction towards P1. In that case, P1 will receive the prefix from P3 color as a label 100, or the number 100. Okay. Last but not least, here I wanted to show you my loopback, which is I think 100. Yeah, loopback 100 in P3. This is the VPN customer that basically we are trying to simulate. So P3 has the IP address 10.1.1.1.1, and P1 has the IP address, which is the loopback 100 as well, 20.1.1.1 for the BRF VPN. Okay. Now we have all that information. We have also perform measurements enabled. Here perform measurement is enabled in P1, for example, in the Giga 000. We have enabled in P1. We have enabled perform measurements in provider 1 as well. In the two interfaces, check the previous video, my last video in the channel, so you will see a bit more information about perform measurements. And also here in this device P3, we have perform measurements enabled. Okay, so how we can make sure again that the latency is being propagated across the whole domain. Also, we saw this command in the previous video, but I just will do real quick. So here in ISIS database in P1, I see my 3 devices. I will just take a look on provider in the middle, the device in the middle. I will take a look what he's advertising. Verbose, detail. He's advertising basically his two physical interfaces. This is one of them, and this is the next one. He's advertising these two physical interfaces, provider 1, basically gigabit 000 and 001. And I just realized here that is wrong the numbering, so sorry for that. So he's advertising both and also the latency, as you can see here, because the latency obviously is gotten from perform measurements, but he's advertising that information into ISIS. If I check the same for provider 3 in P1, show ISIS database, verbose, detail, we have exactly the same. P3 is advertising his physical interface gigabit 000 and the latency over there as well. Okay, so both devices are advertising their latency across the ISIS network. Now, let me check how my SRTE topology looks like, because the SRTE topology basically is a separate database which is fed by ISIS, right? So we need to check in order to make sure that every device from SRTE or segment routing perspective knows all the network. We need to check this topology, okay? And the way to check this topology is show ISIS segment routing, show segment routing traffic engineering topology. So here we see that there are a lot of information. The topology database, where is the source of information that in this case P1 will use to create the SRTE policies. So P1 has in his database the node 1, node 2, and node 3, which basically are the three nodes that we are talking about, okay? In node 1, he has also here, which is basically P1, he has two interfaces. Sorry, this node 1 is a provider 1, is the device in the middle, hostname provider. So he has two interfaces, which are basically the two physical interfaces, and he knows the bandwidth, but also he knows the latency. Look at this, because this is very important. Provider 1 is advertising his latency on this particular link, and also in the other one. This is basically 1793 microseconds, okay? It's the minimum latency, and these two are minimum latency of perform measurements. Remember that with the command show perform measurements interface, we see different latency, minimum, maximum, average. This is the minimum one, okay? Node 2, which is basically provider 3, is advertising also the latency, and node 3, which basically we are that node, we are advertising also the latency. With this command, I am sure that if I enable perform measurements, an SRT policy for the color 100 for the low latency, I am sure that it will work and it will calculate the low latency path. Why? Because I see the devices are exporting the latency across every link. So every time that if you have a segment routing not working, always make sure that the database is fed, okay? Now, how to configure ODN? We need to basically go to segment routing, traffic engineering, on demand, here, color 100, dynamic, and here we need to type metric type latency. That's all what we need for configuring basically ODN for the prefixes or that are being received with the color 100, okay? So that's all the configuration that we need. Now, just to explain more about this color 100, which basically we already touched in here, P3 is in his IVGP sessions towards P1, right? We saw that there is a raw policy that is coloring the prefix with 100, okay? And is sending over BGP. This is very important because P1 is using that color 100, is receiving, of course, this color 100 under BGP, and is using this color for creating the ODN policy and basically telling that it should go over the low latency path across the core. So basically over these three links, okay? Now we will check that P1 is essentially receiving this color before we do commit to this, okay? Do show BGP, BRF, VPN. Let's take a look basically which prefixes we have. So we have many prefixes. 10110 is the one that we received from PE3. So we will take a look on this. And here we see that there is the color 100, right? We have the show command for BGP, and we see the color 100 received as well. And this color 100 is the one basically that we are configuring here. So in a nutshell, this prefix 101110 will be influenced by this SRTE policy. Okay, so let's commit the configuration. We have our ODN configured, and let's verify that ODN policy is up and running. And here we have, with the command show segment routing traffic engineering policy color 100, we see that our policy is up. Both of them are up. Basically, the path to take is the adjacency seed, which is this link here, to go to PE provider 1, and the other is the prefix seed to go to PE3. Okay, and we see the name that is created by default towards the next hop that is 3333. Okay, so this basically tells us that the policies are instantiated. The most important here is the latency. Okay, the latency is the metric that is being used to implement this segment routing traffic engineering policy, and the accumulated delay or latency is this one here that you can see over here. Okay, another important thing is that this segment routing traffic engineering policy has a binding seed 24004. Okay, so when we type show ceph brf VPN towards the prefix from P3/24, we can see here that the label is actually 24004. We explained this in the previous videos, but I always like to recall this. This prefix or the label here that is the same as the binding seed of the SRT policy helps to map basically in Ceph the SRT policy. So Ceph, of course, use the label, and this label is referencing basically the segment routing traffic engineering policy that has been created. And here, of course, how we know that the traffic is going over the path by the segment routing traffic engineering policy. Well, in show ceph, we should see the binding seed. This is verification number 1 here as well. And also the next hop should be the naming that has been created on the segment routing traffic engineering policy. Okay? And specifically, the binding seed is the most important one. It's giving us the mapping of the SRT policy. Okay, so without adding more, this was the lab about how we can create easily our segment routing traffic engineering policies by using the feature perform measurements. It was an easy lab with 3 devices with basically just one path, but I wanted to show you how this works in an easy way. Okay, in the next videos we will look into more options and more paths, so it can be a little bit more interesting also in the case of link failure scenarios, which basically is very interesting when we have low latency as a metric. I hope you enjoyed the video and you learned something. See you in the next one. Thank you very much.